Picture this. You're scrolling through satellite imagery of the ocean floor off the coast of Spain when something stops you cold. Geometric patterns, concentric circles, structures that shouldn't exist beneath thousands of years of sediment. What if I told you these aren't random geological formations, but the remnants of something far more extraordinary? What if the stories we've dismissed as mythology actually preserve the memory of humanity's greatest tragedy? 12,900 years ago, our planet experienced one of the most dramatic climate reversals in recorded geological history. The Younger Dryas period didn't just bring cold weather. It brought catastrophic floods, continental wildfires, and mass extinctions that reshaped the face of Earth itself. But here's the question that keeps researchers awake at night. What if this wasn't just a natural disaster? What if it was the end of everything we thought we knew about human civilization? Welcome back to the channel, where we dive deep into the mysteries that mainstream science prefers to keep buried. I'm your host, and today we're exploring one of the most controversial theories in archaeology. The idea that an advanced civilization, perhaps more sophisticated than our own, was completely erased from history by the catastrophic floods and climate chaos of the Younger Dryas period. Now, before you click away thinking this is just another Atlantis fantasy, I want you to consider something. The evidence we're about to examine isn't coming from fringe theorists or ancient astronaut enthusiasts. It's emerging from peer-reviewed studies, deep-sea exploration missions, and archaeological sites that are forcing us to reconsider everything we thought we knew about our past. Because what if the great flood stories found in cultures across the globe aren't just myths passed down through generations? What if they're historical accounts of the day civilization as we knew it came to an end? The Younger Dryas period lasted roughly 1,300 years, from about 12,900 to 11,550 years ago. To put that in perspective, imagine if our entire industrial civilization, from the steam engine to smartphones, was compressed into just over a millennium. Then imagine it all disappeared in a matter of decades, leaving only scattered survivors to rebuild from scratch. That's the scale of disruption we're talking about. Here's where things get interesting. Traditional archaeology tells us that during this period, humans were simple hunter-gatherers, living in small nomadic groups, barely surviving the harsh conditions. We're told that complex civilization didn't emerge until thousands of years later, with the rise of agriculture in places like Mesopotamia. But what if that timeline is completely wrong? Recent discoveries are painting a very different picture. Take Göbekli Tepe in Turkey, for instance. This massive stone complex, featuring carved pillars weighing up to 20 tons each, was built right at the end of the Younger Dryas period. The precision of its construction, the sophistication of its astronomical alignments, and the sheer scale of the undertaking suggest a level of organization and knowledge that simply shouldn't have existed according to conventional timelines. But Göbekli Tepe might not be the beginning of something new. It might be the last gasp of something much older. What if these monuments weren't built by hunter-gatherers celebrating the dawn of civilization, but by survivors desperately trying to preserve the knowledge of a world that was dying around them? The geological evidence for catastrophic flooding during the Younger Dryas is overwhelming. We're talking about meltwater pulses that raised global sea levels by dozens of meters in just a few centuries. Massive glacial lakes, some larger than all the Great Lakes combined, burst their ice dams and sent torrents of fresh water cascading into the oceans. The sheer volume of water involved defies imagination. Now here's the critical question. Where would an advanced civilization have built its cities? Just like today, they would have chosen coastal areas, river deltas, strategic locations near water sources for trade and transportation. In other words, exactly the places that would have been completely submerged when those massive floods hit. Think about our own civilization for a moment. If sea levels rose by 40 meters tomorrow, what would be left? New York, London, Tokyo, Hong Kong, gone. The vast majority of human infrastructure, knowledge, and population centers would disappear beneath the waves. Future archaeologists might find scattered remnants in the mountains and highlands, but the true heart of our technological civilization would be lost forever under miles of ocean sediment. This brings us to one of the most intriguing pieces of evidence: the black mats. These are dark, carbon-rich layers found at archaeological sites across North America, Europe, and even parts of Asia, all dating to the beginning of the Younger Dryas period. They're packed with charcoal, soot, and microscopic particles that suggest massive, continent-spanning wildfires. But these aren't ordinary fire signatures. Mixed in with the carbon are tiny diamonds, nanodiamonds, that only form under extreme pressure and temperature conditions. We're talking about the kind of forces you'd expect from a massive impact event or explosion. There are also elevated levels of iridium and platinum, elements that are rare on Earth but common in comets and asteroids. What could cause such widespread destruction? One hypothesis that's gaining traction among researchers is that Earth encountered a swarm of comet fragments around 12,800 years ago. These fragments didn't necessarily create massive craters. Many may have exploded in the atmosphere, creating devastating airbursts that ignited the surface below and sent shockwaves around the globe. Imagine multiple nuclear bomb-scale explosions occurring simultaneously across different continents. The immediate effects would be catastrophic. Massive wildfires, atmospheric heating followed by rapid cooling as debris blocked sunlight, and the sudden melting of ice sheets from the thermal pulse. This could explain both the fire signatures we see in the geological record and the rapid climate change that followed. But here's where the story gets even more compelling. If such an event occurred, it would have disproportionately affected the very areas where we'd expect to find evidence of advanced civilization. Coastal regions would have been hit by massive tsunamis. River valleys would have been scoured by unprecedented floods. Any settlements in these prime locations would have been obliterated, their remains buried under meters of sediment or washed out to sea. Recent underwater surveys are beginning to reveal structures that don't fit our current understanding of prehistoric human capabilities. Off the coast of Spain, sonar has detected what appear to be artificial formations with geometric patterns reminiscent of ancient descriptions of Atlantis. Near Australia, vast submerged landscapes have been mapped that could have supported hundreds of thousands of people before being claimed by rising seas. These discoveries are forcing archaeologists to confront an uncomfortable possibility that we may have been looking for evidence of advanced prehistoric civilization in all the wrong places. While we've been excavating highland sites and cave dwellings, the refugees where survivors might have fled, the real centers of population and technology lie buried beneath hundreds of feet of ocean water. The implications are staggering. If an advanced civilization did exist before the Younger Dryas catastrophe, it would mean our understanding of human development needs to be completely rewritten. It would explain the sudden appearance of complex knowledge in various fields, astronomy, mathematics, agriculture, metallurgy, that seems to emerge almost fully formed in the archaeological record. Consider the precision of ancient monuments like the pyramids, Stonehenge, or the megaliths of South America. The mathematical knowledge required for their construction, the sophisticated understanding of astronomy they demonstrate, the engineering techniques needed to move and position massive stone blocks. These achievements appear almost overnight in the historical record, with very little evidence of the gradual development you'd expect. What if this knowledge wasn't developed from scratch by early civilizations, but was instead inherited from survivors of a much older, more advanced culture? What if the priests and scholars of ancient Egypt, Mesopotamia, and other early civilizations were working from incomplete fragments of a much larger body of knowledge that had been largely destroyed in the Great Catastrophe? This would explain one of archaeology's greatest mysteries. Why so many ancient cultures, separated by vast distances and thousands of years, share remarkably similar myths about a great flood that destroyed the world? The Epic of Gilgamesh, the biblical story of Noah, Hindu accounts of cosmic deluges, Native American flood traditions, Aboriginal Australian Dreamtime stories of rising seas. These aren't independent mythologies. They're cultural memories of the same catastrophic event. But if this theory is correct, it raises profound questions about the nature of human progress itself. We tend to think of civilization as a steady upward climb from primitive beginnings to our current technological sophistication. But what if history is actually cyclical? What if humanity has reached great heights before, only to be knocked back to the Stone Age by planetary catastrophes? The evidence we've been discussing suggests that around 12,800 years ago, something fundamentally changed the trajectory of human civilization. Whether it was a cosmic impact, massive volcanic eruptions, or some other catastrophic event, the result was the same. A global reset that erased most traces of whatever had come before and forced the survivors to start over from scratch. In our next segment, we're going to dive deeper into the specific evidence for this lost civilization. We'll examine the mysterious structures being discovered on ocean floors around the world, explore the advanced knowledge that seems to appear suddenly in the archaeological record, and investigate the possibility that some of our most ancient monuments were actually built not by primitive peoples, but by the last survivors of humanity's first golden age. Because if this theory is correct, it doesn't just change our understanding of the past, it fundamentally alters how we think about our future. If advanced civilizations can rise and fall, leaving barely a trace behind, what does that mean for our own technological society? Are we living through humanity's second attempt at reaching for the stars? And if so, what can we learn from the fate of those who came before us? The answers to these questions are buried not just in ancient sediment and ocean floors, but in the very foundations of human knowledge itself. And as we're about to discover, the more we dig, the more mysterious our origins become. The archaeological evidence for this lost civilization becomes even more compelling when we examine the sheer impossibility of what we're seeing in the geological record. Picture walking through a museum where every exhibit challenges everything you thought you knew about human history. That's exactly what researchers are experiencing as they uncover layer after layer of anomalous evidence from the Younger Dryas boundary. Let's start with something that should make every scientist pause and reconsider our timeline: the speed of technological development that occurred immediately after this catastrophic period. According to mainstream archaeology, humans went from simple hunter-gatherers to builders of massive stone complexes in what amounts to an evolutionary blink of an eye. We're talking about a transition that supposedly happened in just a few centuries. But here's what doesn't add up. The level of sophistication displayed in sites like Göbekli Tepe isn't primitive or experimental. These aren't the fumbling first attempts of people learning to work with stone. The craftsmanship is masterful, the planning is meticulous, and the execution is flawless. It's like finding a perfectly functioning smartphone in a medieval castle. The technology exists, but it shouldn't according to our understanding of how civilizations develop. The mathematical precision alone should give us pause. The pillars at Göbekli Tepe are arranged in perfect circles, with astronomical alignments that demonstrate a sophisticated understanding of celestial mechanics. The builders knew exactly how to calculate angles, create perfect geometric forms, and orient their structures to track the movement constellations. This isn't knowledge of stars and that emerges overnight among nomadic peoples struggling to survive in a harsh, post-glacial world. What we're seeing looks suspiciously like inherited knowledge. Techniques and understanding passed down from an earlier, more advanced civilization. Think about it this way. If our modern world suddenly collapsed tomorrow and only scattered survivors remained, they might still retain fragments of scientific knowledge, engineering principles, and mathematical concepts. They might not be able to rebuild our smartphones or space stations immediately, but they could potentially construct impressive monuments that would puzzle future archaeologists. This brings us to one of the most disturbing aspects of the evidence we're uncovering. The distribution of these anomalous sites isn't random. They're found in highland areas, mountain regions, and elevated plateaus, exactly where you'd expect survivors of a massive flood to have fled. Meanwhile, the vast coastal plains and river valleys, where we'd expect to find evidence of large-scale civilization, remain buried under hundreds of feet of sediment or lost beneath the waves. Recent advances in underwater archaeology are beginning to reveal the true scope of what we've lost. The submerged landscapes off northern Australia alone cover an area larger than many modern countries. Before sea levels rose, this was dry land with rivers, valleys, and ecosystems that could have supported massive populations. Stone tools and other artifacts have already been recovered from these depths, proving that humans were living and working in these areas before they were claimed by the rising waters. But we're not just talking about simple fishing villages or temporary camps. The scale of some underwater formations suggests something far more sophisticated. Sonar imaging has revealed linear features, geometric patterns, and what appear to be artificial structures extending for miles across the ocean floor. While natural processes can create some remarkable formations, the regularity and precision of these features is difficult to explain without human intervention. The timing of these discoveries is particularly significant. The areas we're mapping were above sea level until the end of the Younger Dryas period, when massive meltwater pulses raised global ocean levels by dozens of meters. This wasn't a gradual process taking millennia. Geological evidence suggests it happened over just a few centuries, with some periods of extremely rapid sea level rise occurring over just decades. Imagine living through such an event. Coastal cities that had existed for thousands of years would have been swallowed by the advancing waters. Entire civilizations would have been forced to abandon their homes, their temples, their centers of learning and government. The survivors would have been refugees, carrying with them only what knowledge they could preserve in their memories and whatever tools they could carry to higher ground. This scenario would explain another puzzling aspect of early post-Younger Dryas archaeology: the apparent sudden appearance of agricultural knowledge in multiple locations around the world. Traditional theories suggest that agriculture was independently invented in several different regions at roughly the same time. But what if it wasn't invented at all? What if it was remembered? Survivors of a flood-devastated coastal civilization would have carried with them the knowledge of plant cultivation, animal domestication, and food preservation techniques. They would have known which grasses could be selectively bred to create more productive grains, which animals could be tamed and bred for specific traits, and how to manage water resources for irrigation. This knowledge wouldn't need to be developed from scratch. It would simply need to be applied to new environments and conditions. The genetic evidence supports this interpretation. The wild ancestors of our most important crop plants, wheat, barley, rice, corn, show signs of having been selectively bred for desirable traits long before the dates traditionally assigned to the beginning of agriculture. It's as if someone already knew what they were looking for and how to achieve it, rather than discovering these techniques through trial and error over many generations. Similarly, the astronomical knowledge embedded in early post-Younger Dryas monuments suggests an understanding of celestial cycles that should have taken centuries of careful observation to develop. Yet these alignments appear fully formed in the archaeological record, as if the builders already possessed sophisticated mathematical and astronomical knowledge from the very beginning. The implications become even more intriguing when we consider the global nature of certain architectural and engineering techniques. The precision cutting and fitting of massive stone blocks, the use of specific geometric proportions, the alignment with celestial bodies. These features appear in monuments built by supposedly unconnected cultures, separated by thousands of miles and hundreds of years. Either we're looking at a remarkable series of coincidences, or we're seeing the fingerprints of a shared knowledge base that predates the isolation of these different civilizations. But perhaps the most compelling evidence comes from the stories themselves. The flood narratives found in cultures around the world don't just describe a generic disaster. They contain specific details that align remarkably well with what we know about the Younger Dryas catastrophe. They speak of fire from the sky, of darkness that lasted for years, of massive floods that covered the highest mountains, and of the few survivors who carried the seeds of civilization to new lands. These aren't vague mythological accounts. They're detailed descriptions of specific events, preserved with remarkable consistency across cultures that had no contact with each other. The Mesopotamian account speaks of Utnapishtim, who saved not just his family, but also craftsmen and artisans, the keepers of knowledge and skills. The Hindu traditions describe Manu, who preserved not just life, but also the sacred knowledge necessary to rebuild civilization. Native American traditions tell of sky beings who taught the survivors how to plant crops and build permanent settlements. What if these weren't gods or mythical figures at all? What if they were the educated survivors of the previous civilization? Scientists, engineers, priests, and scholars who managed to escape the catastrophe and dedicated their lives to preserving and passing on whatever knowledge they could salvage from the ruins of their world. This interpretation would explain why early civilizations seemed to emerge with such sophisticated knowledge already in place. They weren't starting from zero. They were building on the remnants of something much older and more advanced. The survivors became the teachers, the wise men, the founding figures of new cultures that carried forward whatever fragments of the old world they could preserve. The question that haunts researchers investigating this possibility is simple yet profound. If we're right, what else are we missing? If an entire advanced civilization could be erased so completely that we're only now beginning to recognize the evidence for its existence, what does that tell us about the fragility of human progress? How many other rises and falls might be hidden in the geological record, waiting for the right technology and the right questions to bring them back to light? As we continue our investigation into this mystery, we'll explore the specific technologies that this lost civilization might have possessed, examine the evidence for their potential level of advancement, and consider what their fate might teach us about our own future. Because if history truly is cyclical, if civilizations can rise to great heights only to be swept away by planetary catastrophes, then understanding what happened during the Younger Dryas isn't just an academic exercise. It's a survival guide for our own species. The story we're uncovering challenges everything we thought we knew about human development, placing the grand, progress, and outward sweep of geological time. And as we're about to discover, the deeper we dig into this mystery, the more questions arise about not just who we were, but who we might become. The evidence becomes even more extraordinary when we examine what researchers are calling the knowledge explosion that occurred immediately following the Younger Dryas period. It's as if someone flipped a switch and suddenly human beings across the globe began displaying capabilities that should have taken millennia to develop. But what if this wasn't the birth of human ingenuity? What if it was its resurrection? Let's talk about metallurgy for a moment. The traditional archaeological timeline suggests that humans gradually learned to work with metals over thousands of years, slowly progressing from simple copper tools to more complex bronze and iron alloys. But when we look at the actual evidence, we find something far more puzzling. Some of the earliest metal objects ever discovered display a level of sophistication that rivals modern techniques. Take the copper pipes found in ancient Chinese sites, dated to shortly after the Younger Dryas period. These aren't crude hammered sheets or simple cast objects. They show evidence of advanced smelting techniques, precise temperature control, and an understanding of metallurgical principles that supposedly wasn't developed until much later. It's like finding a perfectly tuned piano in a cave dwelling. The technology exists, but according to our timeline, it shouldn't. The same pattern emerges in astronomy. The builders of early monuments like Newgrange in Ireland or the stone circles of Britain demonstrated an understanding of celestial mechanics that required centuries of careful observation and mathematical calculation. They knew about the precession of equinoxes, understood complex lunar cycles, and could predict eclipses with remarkable accuracy. This wasn't primitive stargazing. This was sophisticated mathematical astronomy. But here's what makes this even more intriguing. These astronomical alignments weren't just decorative or ceremonial, they were functional. Many of these monuments served as precise calendars, allowing their builders to track seasonal changes, predict optimal planting times, and coordinate large-scale agricultural activities. This suggests not just knowledge of the stars, but a deep understanding of how celestial cycles affected terrestrial agriculture, knowledge that would have been absolutely critical for survivors trying to establish new agricultural settlements after a global catastrophe. Consider what would happen if our modern civilization suddenly collapsed. The survivors would still retain fragments of scientific knowledge. They might remember the periodic table, understand basic principles of physics, or recall mathematical formulas. But they would lack the infrastructure to immediately rebuild our technology. Instead, they would focus on the most essential applications of this knowledge: how to purify water, how to predict weather patterns, how to calculate the best times for planting crops. This is exactly what we see in the archaeological record following the Younger Dryas. The knowledge that appears isn't random or experimental. It's precisely the kind of information that would be most crucial for rebuilding civilization from scratch. Agricultural techniques, astronomical calculations for timing, basic metallurgy for tools, and sophisticated engineering for permanent structures. The distribution of this knowledge is equally telling. Rather than emerging in one location and gradually spreading, these techniques appear almost simultaneously in widely separated regions around the globe. It's as if multiple groups of survivors, scattered by the catastrophe, were all drawing from the same reservoir of inherited knowledge and adapting it to their new environments. This brings us to one of the most remarkable discoveries of recent years: the extent of the underwater landscape that was lost when the ice sheets melted. We're not talking about small coastal areas or isolated islands. We're talking about land masses comparable in size to entire continents. The Sahel Shelf, connecting Australia and New Guinea, the Beringia land bridge between Asia and North America, the vast plains of Doggerland that once connected Britain to Europe. All of these were dry land during the Ice Age, and all were claimed by rising seas during the Younger Dryas melt. But perhaps the most significant lost landscape is one that most people have never heard of: the continental shelf areas that surrounded every landmass on Earth. These weren't barren tundra or inhospitable wasteland. They were temperate, fertile plains with rivers, lakes, and ecosystems that could have supported massive populations. When the ice melted and sea levels rose by over 100 meters, these areas, which represented roughly a quarter of all the land surface available during the Ice Age, simply vanished beneath the waves. To put this in perspective, imagine if a quarter of all land on Earth today suddenly disappeared underwater. Every coastal city, every river delta, every fertile plain within 100 kilometers of the current shoreline, gone. The human displacement would be unimaginable. The loss of infrastructure, knowledge, and cultural continuity would set our species back by millennia. This is exactly what happened during the Younger Dryas melt, and it explains why the archaeological record shows such a dramatic discontinuity. We're not just missing evidence of advanced prehistoric civilization. We're missing the evidence because it's buried under hundreds of feet of ocean sediment, or scattered across the abyssal plains of the deep sea. Recent underwater surveys are beginning to reveal the scope of this loss. Off the coast of India, researchers have discovered what appear to be ancient river channels extending for hundreds of kilometers across the ocean floor. These channels show clear evidence of having carried fresh water, suggesting they were once part of a vast terrestrial landscape with flowing rivers and established watersheds. Similar discoveries are being made around the world. Off Japan, underwater formations display geometric patterns that are difficult to explain through natural processes alone. Near the Bahamas, precise rectangular structures have been mapped on the sea floor, their straight edges and right angles suggesting artificial construction. And off the coast of Spain, the concentric circular formations that initially sparked our investigation continue to yield new details with each passing survey mission. What makes these discoveries particularly compelling is their context within the broader pattern of evidence we've been discussing. They're located in exactly the areas where we would expect to find the centers of an advanced maritime civilization. Strategic locations near river mouths, in protected harbors, along major coastal trade routes. These weren't random settlements scattered across the landscape. They appear to represent carefully chosen locations that would have been ideal for supporting large, sophisticated communities. The implications are staggering. If even a fraction of these underwater formations proved to be artificial constructions, it would mean that human civilization achieved levels of complexity and sophistication thousands of years earlier than previously thought. It would mean that the rise of agriculture, the development of cities, and the emergence of complex societies weren't unique achievements of the post-glacial world, but were actually the second time humanity had reached such heights. This interpretation would explain one of archaeology's most persistent mysteries: the apparent sudden appearance of fully formed civilizations in the historical record. Places like Sumer, the Indus Valley, and ancient Egypt don't show the gradual development you'd expect from societies learning to build cities from scratch. Instead, they appear with sophisticated knowledge of urban planning, complex religious and governmental systems, an advanced understanding of mathematics, astronomy, and engineering already in place. What if these civilizations weren't starting fresh, but were rebuilding based on inherited knowledge and techniques passed down from the survivors of the previous world? What if the priests of ancient Egypt, the scholar kings of Mesopotamia, and the builders of the Indus Valley cities were working from incomplete but still sophisticated fragments of a much larger body of knowledge that had been largely lost in the Great Catastrophe? The timeline certainly supports this interpretation. The major civilizations we recognize as the beginning of recorded history all emerged within a relatively narrow window following the end of the Younger Dryas period. It's as if there was a recovery period of several thousand years during which scattered survivor populations slowly grew and consolidated, and then suddenly multiple advanced civilizations appeared almost simultaneously around the globe. But if this theory is correct, it raises profound questions about the nature of human progress and the stability of technological civilization. We tend to think of our current world as the pinnacle of human achievement, the natural culmination of a steady upward climb from primitive beginnings. But what if we're actually living through humanity's second attempt at reaching advanced technological capability? What if the first attempt was cut short by planetary catastrophe, leaving only fragmented memories and inherited techniques to guide the survivors in their efforts to rebuild? The evidence suggests that around 12,800 years ago, something fundamental changed in Earth's climate system with such speed and violence that it reset human civilization entirely. Whether it was cosmic impacts, massive volcanic eruptions, or some other catastrophic trigger, the result was the same: a global catastrophe that erased most traces of whatever had come before and forced the survivors to start over from scattered fragments. Understanding what happened during this period isn't just an academic exercise in reconstructing ancient history. If civilizations can rise to great heights and then be swept away by planetary forces beyond their control, it forces us to confront uncomfortable questions about our own future. Are we building on foundations that are more fragile than we realize? Have we learned enough from the past to avoid repeating the mistakes that may have doomed our predecessors? As we continue to uncover evidence of this lost world, we're not just reconstructing the past, we're potentially uncovering a preview of patterns that could repeat themselves. the forces that shaped the Younger Dryas period. Climate instability, cosmic impacts, massive geological changes are still active today. The question isn't whether such events could happen again, but whether we'll be better prepared to survive them when they do. In our next exploration of this mystery, we'll examine the specific technologies this lost civilization may have possessed, investigate the evidence for their potential level of advancement, and consider what their ultimate fate might teach us about building a more resilient future for our own species. Because if the evidence is pointing us toward the truth, then the story of the Younger Dryas catastrophe isn't just ancient history. It's a warning about the cycles of rise and fall that may define the long-term trajectory of human civilization itself. The more we uncover about this vanished world, the more we realize that our current understanding of human development may be fundamentally incomplete. We may not be the first technological civilization this planet has seen, and if current trends continue, we may not be the last. The question is whether we can learn from the fate of those who came before us, or whether we're destined to repeat the same cycle of advancement and catastrophic collapse that seems to define the deeper patterns of human history. The deeper we dive into this mystery, the more we begin to understand that we're not just looking at scattered archaeological anomalies. We're potentially staring at the remnants of humanity's greatest lost chapter, and the implications are absolutely mind-bending. Here's where things get really interesting. When we start mapping out the locations of these mysterious underwater structures, a clear pattern emerges. They're not randomly scattered across the ocean floors like you'd expect from natural formations. Instead, they cluster around what would have been strategic maritime locations during the Ice Age: natural harbours, river mouths, and key points along ancient coastlines that are now hundreds of feet underwater. Think about how our modern civilization is organised. Our major cities aren't built in random locations. They're positioned at crucial transportation hubs, natural ports, river confluences, and resource-rich areas. If you were to design the optimal locations for a maritime trading civilization 12,000 years ago, you'd choose exactly the spots where these underwater anomalies are now being discovered. But here's what should really make your skin crawl with excitement. The sophistication of some of these formations suggests they weren't just simple coastal settlements. We're talking about structures that show evidence of large-scale engineering projects, breakwaters, harbour installations, and what appear to be systematic modifications to natural coastlines to create protected anchorages. This level of coastal engineering requires not just advanced knowledge of maritime construction, but also a deep understanding of ocean currents, tidal patterns, and long-term geological stability. You don't undertake projects of this magnitude unless you're planning for permanence. These weren't temporary fishing camps or seasonal settlements. These were the infrastructure investments of a civilization that expected to be around for centuries. Now, let's talk about something that's been bothering researchers for decades: the sudden appearance of sophisticated nautical knowledge in the archaeological record. Ancient civilizations demonstrated an understanding of navigation, shipbuilding, and ocean travel that seems to emerge fully formed, without the gradual development you'd expect from people slowly learning to work with boats and coastal waters. The Polynesians somehow managed to navigate across thousands of miles of open ocean using techniques that modern sailors struggle to replicate. Ancient Egyptian and Mesopotamian texts describe vessels and maritime expeditions that suggest knowledge of advanced navigation techniques. Even landlocked civilizations show evidence of understanding oceanic cycles and coastal phenomena that they shouldn't have known about if they were truly isolated from maritime culture. What if this knowledge wasn't developed independently by these various civilizations? What if they inherited it from survivors who had once been part of a sophisticated maritime society that spanned the globe's ancient coastlines? The navigational techniques, the understanding of ocean currents, the knowledge of seasonal wind patterns, all of this could have been preserved and passed down by refugees from the drowned world. This brings us to one of the most fascinating aspects of the evidence we're uncovering: The timeline of technological development following the Younger Dryas doesn't show the gradual, experimental progression you'd expect from societies learning new skills from scratch. Instead, it shows rapid implementation of sophisticated techniques that suggest people already knew what they were trying to achieve. Consider pottery, for instance. The earliest ceramic vessels discovered in post-Younger Dryas sites aren't crude, experimental attempts at making containers. They show sophisticated understanding of clay composition, firing temperatures, and decorative techniques. It's as if the makers already possessed a comprehensive knowledge of ceramic technology and were simply adapting it to new materials and local conditions. The same pattern appears in textile production. Early fabrics show evidence of complex weaving techniques, understanding of fiber properties, and sophisticated dyeing methods. These aren't the fumbling first attempts of people learning to work with plant and animal fibers. They demonstrate expertise that would normally take generations to develop through trial and error. But perhaps the most compelling evidence comes from the astronomical alignments built into monuments constructed immediately after the catastrophic period. These structures don't just show awareness of celestial cycles, they demonstrate precise mathematical understanding of complex astronomical phenomena that require centuries of careful observation to detect and calculate. The builders of these monuments knew about the precession of equinoxes, a cycle that takes over 25,000 years to complete. They understood the intricate dance of lunar cycles and could predict eclipses with remarkable accuracy. They incorporated knowledge of stellar positions and planetary movements that suggests access to astronomical records spanning multiple millennia. Here's the thing that keeps researchers up at night. You can't develop this level of astronomical sophistication in just a few centuries. The observations required to understand precession alone would take multiple generations of dedicated sky watchers, carefully recording and comparing data over hundreds of years. Yet this knowledge appears in the archaeological record as if it was already fully developed and understood. The only logical explanation is that this astronomical knowledge was inherited from an earlier civilization that had been conducting systematic observations for thousands of years before the catastrophe struck. The monument builders weren't discovering these celestial patterns. They were encoding ancient knowledge into stone to ensure it would survive future disasters. This interpretation gains even more credibility when we examine the global distribution of certain astronomical alignments. Monuments separated by thousands of miles and built by supposedly unconnected cultures show remarkably similar orientations and mathematical relationships. Either we're looking at an extraordinary series of coincidences, or we're seeing evidence of a shared knowledge base that predated the isolation of these different civilizations. The mathematics alone should give us pause. The geometric relationships built into ancient monuments demonstrate understanding of advanced mathematical concepts that supposedly weren't developed until much later in human history. We're talking about precise ratios, complex geometric forms, and mathematical relationships that require sophisticated computational abilities to calculate and implement. Take the golden ratio, for instance. This mathematical relationship appears in monuments and artifacts from cultures that supposedly had no contact with each other. Yet they all somehow discovered and implemented the same mathematical constant with remarkable precision. The probability of this happening independently across multiple unconnected civilizations is so small as to be essentially impossible. What we're seeing looks like fragments of a much larger mathematical and scientific knowledge base that was scattered across the globe by the catastrophe. Different survivor groups preserved different pieces of this knowledge, adapting and implementing what they remembered in their new environments and circumstances. This fragmentation would explain why early post-catastrophe civilizations show such uneven development. They might possess sophisticated astronomical knowledge, but lack advanced metallurgy. They might demonstrate remarkable engineering capabilities, but show gaps in other technical areas. It's as if they were working from incomplete textbooks, trying to rebuild complex systems based on fragmentary memories and partial understanding. The linguistic evidence supports this interpretation as well. When researchers trace the roots of ancient languages, they find unexpected connections between cultures that supposedly developed in isolation. Mathematical and technical terms, in particular, show remarkable similarities across widely separated civilizations, suggesting they may have inherited these concepts from a common source. But here's where the story takes a darker turn. If this lost civilization was as advanced as the evidence suggests, why did it disappear so completely? What could cause such total destruction that an entire technological society could be erased from the geological record, leaving only scattered survivors to carry forward fragments of their knowledge? The answer may lie in the very success of their maritime orientation. A civilization that built its major centers along ancient coastlines would have been perfectly positioned to take advantage of Ice Age geography. The lower sea levels would have exposed vast continental shelves, creating extensive coastal plains ideal for agriculture, transportation, and trade. Rivers would have been longer, providing more navigable waterways. Natural harbours would have been larger and more numerous. But this same coastal orientation would have made them incredibly vulnerable to the rapid sea level rise that occurred during the Younger Dryas melt. When the ice sheets began collapsing and massive volumes of meltwater poured into the oceans, their thriving coastal cities would have been the first casualties. The very geography that had made their civilization possible became the instrument of its destruction. The speed of this change cannot be overstated. Geological evidence suggests that some periods of sea level rise during the Younger Dryas melt occurred at rates of several meters per century, fast enough that coastal settlements would have been abandoned within a single human lifetime. Entire generations would have watched their ancestral lands disappear beneath the waves, forced to retreat inland, carrying only what knowledge and portable artifacts they could salvage from their drowning world. This scenario would explain the curious mixture of advanced knowledge and apparent technological regression that we see in early post-catastrophe civilizations. The survivors would have retained theoretical understanding of sophisticated concepts, mathematics, astronomy, engineering principles, but they would have lost the infrastructure and accumulated resources necessary to immediately implement these technologies at their previous scale. Imagine if our modern world suddenly lost all of its manufacturing facilities, power grids, and resource extraction networks, but some of the population survived with their scientific knowledge intact. The survivors might understand nuclear physics and computer science, but they would be reduced to farming with hand tools and building with stone and wood until they could slowly reconstruct the industrial base necessary to support advanced technology. This is precisely what we see in the archaeological record following the Younger Dryas catastrophe. Sophisticated knowledge preserved in fragmentary form, gradually being re-implemented as survivor populations grew and developed the resources necessary to undertake large-scale construction projects and technological development. The implications of this interpretation extend far beyond archaeology and ancient history. If advanced civilizations can be so completely erased by planetary catastrophes that we're only now beginning to recognize evidence of their existence, what does this tell us about the long-term stability of our own technological society? We pride ourselves on the permanence of our achievements, our cities, our knowledge bases, our technological infrastructure, but the evidence from the Younger Dryas suggests that even highly advanced civilizations can be reduced to scattered survivors in the space of just a few centuries. The monuments we build, the cities we construct, the knowledge we accumulate, all of it could potentially be swept away by forces beyond our control, leaving only fragments for future archaeologists to puzzle over. This realization should fundamentally change how we think about preserving human knowledge and capability across potential future catastrophes. If planetary disasters are cyclical rather than random, if civilizations have risen and fallen multiple times in our species' history, then we need to start thinking seriously about how to ensure that essential knowledge and technologies can survive potential collapses and be transmitted to future recovery efforts. The story we're uncovering isn't just about what happened 12,000 years ago. It's a preview of patterns that may define the long-term trajectory of human civilization itself. The question isn't whether planetary catastrophes will occur again. The geological record makes it clear that they will. The question is whether we'll be better prepared to preserve and transmit our achievements across the gaps in continuity that such events inevitably create. As we continue to decode the mystery of this lost civilization, we're not just reconstructing ancient history, we're potentially uncovering a survival guide written in stone and sediment by our own species' previous attempts to build lasting technological societies. And if we're smart enough to read the lessons they left behind, we might just avoid repeating the same tragic cycle of advancement and catastrophic loss that seems to have defined human development across much deeper timescales than we ever imagined possible. The evidence keeps mounting, and with each new discovery, the picture becomes clearer. We may not be the first technological civilization this planet has seen, and unless we learn from the fate of our predecessors, we may not be the last. The choice of whether to break this cycle or repeat it may be the most important decision our species will ever make. The technological sophistication we're beginning to understand about this lost civilization becomes even more extraordinary when we examine what researchers are calling the precision paradox. These aren't just impressive monuments built by skilled craftsmen. We're looking at evidence of manufacturing capabilities that challenge our fundamental assumptions about prehistoric human abilities. Let's talk about something that should make every engineer's jaw drop. Stone cutting techniques found at sites dating to immediately after the Younger Dryas period show precision that rivals modern machine tooling. We're talking about perfectly straight cuts through the hardest granite, surface finishes that are smooth to within microscopic tolerances, and joints between massive blocks that are so precise you can't slide a piece of paper between them. But here's what makes this truly mind-bending. These aren't isolated examples found at one or two sites. This level of stoneworking precision appears simultaneously across multiple continents, in locations that supposedly had no contact with each other. The mathematical accuracy, the consistency of techniques, the sophisticated understanding of material properties. It's as if multiple groups of survivors were all working from the same advanced technical manual. Consider what it would take to achieve this level of precision using the tools that mainstream archaeology attributes to these periods. We're told these monuments were built by people using copper chisels, wooden levers, and rope. Try to imagine cutting granite blocks weighing dozens of tons to tolerances measured in fractions of millimeters using such primitive tools. It's not just difficult, it's essentially impossible. Yet the evidence is right there in front of us. Blocks that have been shaped with mathematical precision, surfaces that show tool marks consistent with high-speed cutting implements, and construction techniques that demonstrate understanding of advanced engineering principles. Either our ancestors possessed technologies we don't know about, or we're looking at the remnants of inherited knowledge from a much more advanced predecessor civilization. The acoustic properties of these monuments provide another layer of mystery. When researchers test the sound characteristics of ancient stone structures, they discover something remarkable. Many of these buildings were designed as sophisticated acoustic instruments, capable of producing specific frequencies and resonant effects that would have required advanced understanding of physics and mathematics to calculate and implement. We're not talking about accidental acoustic effects that happen to emerge from random construction techniques. These are precisely engineered sound chambers designed to amplify certain frequencies while dampening others. The mathematical relationships between chamber dimensions, the careful placement of resonating surfaces, the strategic positioning of sound-focusing elements. This represents a level of acoustic engineering that we've only recently learned to achieve with computer modeling and advanced materials science. What makes this even more intriguing is the consistency of certain acoustic frequencies across monuments built by different cultures in different time periods. Specific sound frequencies appear again and again in structures separated by thousands of miles and hundreds of years. Either ancient builders independently discovered the same optimal acoustic relationships through trial and error, which seems highly unlikely. Or they were working from shared knowledge of acoustic principles that had been developed by an earlier, more scientifically advanced civilization. The implications go even deeper when we consider the potential purposes of these acoustic effects. Modern research into sound frequencies and their effects on human consciousness suggests that certain vibrations can induce altered states of awareness, promote healing responses, and even affect cognitive function. If the builders of these monuments understood these principles, it would indicate a level of knowledge about human physiology and neuroscience that supposedly wasn't developed until the modern era. But perhaps the most compelling evidence for advanced prehistoric technology comes from an unexpected source: the precision of astronomical observations encoded in ancient monuments. When researchers calculate the exact positions of stars and planets at the time these structures were built, they discover something that should be impossible. The builders weren't just observing celestial objects. They were making measurements accurate to fractions of degrees. This level of astronomical precision requires sophisticated measuring instruments. You can't track stellar positions to the accuracy we see in these monuments using naked eye observation alone. The measurements would require telescopic precision, mathematical calculation of atmospheric refraction effects, and long-term tracking of subtle celestial movements that are barely detectable without advanced instrumentation. Yet somehow, builders working thousands of years ago achieved measurement accuracy that rivals modern astronomical equipment. They tracked the precession of equinoxes with mathematical precision, calculated planetary positions centuries into the future, and encoded complex astronomical relationships into their monuments with an accuracy that we can barely match today. The only logical explanation is that they possessed measuring instruments and calculation methods far more sophisticated than anything mainstream archaeology attributes to prehistoric civilizations. But where are these instruments? Where is the evidence of the advanced manufacturing capabilities that would have been necessary to create such precision tools? The answer may lie in the very completeness of the catastrophe that destroyed their civilization. If their primary centers were coastal cities that were completely submerged by rising seas, then their workshops, their laboratories, their libraries, and their precision instruments would all be buried under hundreds of feet of ocean sediment. We're not finding evidence of their advanced technology because it's lying on the deep ocean floor, scattered across abyssal plains that we've barely begun to explore. Recent developments in deep-sea archaeology are starting to change this picture. Advanced submersibles and underwater survey equipment are beginning to reveal artificial structures in locations that were dry land during the Ice Age. But the scale of the area that needs to be explored is staggering. We're talking about searching an area equivalent to several continents, buried under sediment layers that have been accumulating for over 12,000 years. The few artifacts that have been recovered from these depths are tantalizing. Worked stone objects with precision surfaces, metal alloys that show sophisticated understanding of metallurgy, and carved objects that demonstrate advanced artistic and technical capabilities. But these are isolated finds of what, scattered fragments, may have been a vast technological civilization. What's particularly intriguing is the evidence for large-scale engineering projects that were apparently undertaken immediately before the catastrophic sea level rise. Geological surveys of drowned coastlines reveal what appear to be massive earthworks, artificial harbours, coastal modifications, and what may have been attempts to create protective barriers against rising waters. These aren't simple construction projects. We're talking about engineering undertakings that would have required coordinated effort by thousands of workers, sophisticated understanding of hydraulic engineering, and advanced planning capabilities. The scale and complexity suggest a civilization with organizational capabilities comparable to our own modern societies. But here's the really disturbing part. Some of these coastal engineering projects appear to have been abandoned before completion. It's as if the builders realized that their efforts couldn't keep pace with the rapidly rising waters and simply gave up, retreating inland and leaving their massive construction projects to be swallowed by the advancing seas. Imagine the desperation of those final generations, watching the waters rise year after year, season after season, throwing all of their civilization's resources into increasingly desperate attempts to hold back the flood, building higher walls, deeper channels, more complex drainage systems, and ultimately realizing that they were fighting forces beyond their control, that their entire world was going to disappear beneath the waves, no matter what they did. The psychological trauma of such an experience would be unimaginable. Entire populations forced to abandon not just their homes, but their entire way of life. The accumulated knowledge and achievements of thousands of years, built up over countless generations, simply washed away by forces they couldn't understand or control. This trauma would explain another puzzling aspect of post-catastrophe archaeology: the apparent obsession with flood narratives and water management systems in early civilizations. These weren't just practical concerns for agricultural societies. They represent deep cultural memories of existential threats, of the day the waters rose and swallowed the world. The survivors would have carried with them not just fragments of technical knowledge, but also a profound understanding of how quickly even the most advanced civilization can be destroyed by planetary forces. This knowledge would have shaped every aspect of their rebuilding efforts, influencing where they chose to settle, how they designed their cities, and what kinds of knowledge they prioritized for preservation. We see evidence of this influence in the locations chosen for major post-catastrophe settlements. Rather than rebuilding along coastlines where their ancestors had thrived, the survivors established their new centers well inland, on elevated ground that would be safe from flooding. They built massive drainage systems and flood control measures that seemed disproportionate to local conditions, as if they were preparing for water management challenges far beyond anything their immediate environment would normally require. But perhaps most tellingly, they invested enormous resources in creating permanent monuments designed to preserve essential knowledge across future catastrophes. The precision of astronomical alignments, the encoding of mathematical relationships in stone, the careful preservation of technical knowledge in symbolic form, all of this represents a civilization-level commitment to ensuring that critical information would survive, even if their society itself didn't. These monuments weren't just religious or ceremonial structures. They were information storage systems, designed to preserve and transmit essential knowledge across the gaps in cultural continuity that catastrophic events inevitably create. The builders had learned from bitter experience that technological civilizations can disappear almost overnight, leaving only scattered survivors to carry forward whatever fragments they can preserve. This interpretation completely changes how we should think about ancient monuments and archaeological sites. Instead of seeing them as the crude first attempts of primitive peoples learning to work with stone, we should recognize them as sophisticated information preservation systems created by survivors who understood all too well how fragile technological civilization really is. The knowledge encoded in these structures represents not the beginning of human scientific understanding, but rather the desperate attempt by catastrophe survivors to preserve fragments of a much larger body of knowledge that had been largely lost in the Great Disaster. They were building libraries in stone, encoding essential information in forms that could survive future floods, earthquakes, and societal collapses. If this interpretation is correct, then we're not just looking at an interesting archaeological mystery. We're staring at evidence of humanity's first great attempt at building a technological civilization, and we're seeing how completely and thoroughly such achievements can be erased by planetary catastrophes. The implications for our own future are sobering. We pride ourselves on our digital information storage systems, our global communication networks, our distributed knowledge bases. But what would happen if sea levels rose by 100 meters over the course of just a few centuries? How much of our accumulated knowledge and technological capability would survive such a catastrophe? The answer suggested by the Younger Dryas evidence is deeply unsettling. Even highly advanced civilizations can be reduced to scattered fragments in remarkably short periods of time. The monuments they build, the cities they construct, the knowledge they accumulate, all of it can be swept away by forces that operate on geological rather than human timescales. But there's also hope in this story. If the survivors of the previous catastrophe manage to preserve enough knowledge to eventually rebuild and create the foundations of our own technological development, then recovery is possible. The question is whether we can learn from their experience and do better at preserving essential knowledge and capabilities across potential future disasters. The evidence suggests that the builders of post-catastrophe monuments understood something we're only beginning to grasp: that technological civilizations are far more fragile than they appear, and that preserving knowledge across catastrophic discontinuities requires deliberate, long-term planning on a scale that transcends individual generations or even individual cultures. As we continue to decode the messages left behind in stone by these ancient knowledge preservers, we're not just reconstructing the past. We're potentially discovering a blueprint for how to build technological civilizations that can survive planetary catastrophes and transmit their achievements across the vast timescales on which such events occur. The story of the Younger Dryas catastrophe and its aftermath isn't just ancient history. It's a preview of challenges that our own civilization may face, and a guide to strategies that might help us navigate such challenges more successfully than our predecessors did. The question is whether we're wise enough to learn from their experience before we're forced to repeat it. The sophistication of these ancient information preservation systems becomes even more remarkable when we examine the mathematical relationships they encode. These aren't random arrangements of stones or arbitrary decorative elements. We're looking at complex geometric formulas, astronomical calculations, and engineering principles embedded in permanent form, designed to be decoded by future generations who might possess the knowledge necessary to understand their significance. Consider the implications of what we're discovering. If a civilization advanced enough to undertake precision engineering projects and conduct sophisticated astronomical observations could be so thoroughly erased that we're only now beginning to recognize their existence, what does that tell us about the assumptions we make regarding historical continuity? The pattern that emerges from the evidence is both fascinating and terrifying. Advanced knowledge appears in the archaeological record not as a gradual development, but as sudden implementation of sophisticated techniques that suggest inherited understanding rather than independent discovery. The survivors weren't starting from zero. They were working with fragmentary memories of much more comprehensive systems. This fragmentation explains one of the most puzzling aspects of early post-catastrophe civilizations: their uneven technological development. A culture might demonstrate remarkable astronomical knowledge while showing apparent gaps in other technical areas. They might possess sophisticated mathematical understanding, but lack certain manufacturing capabilities. It's as if they were working from incomplete instruction manuals, trying to reconstruct complex systems based on partial information. The linguistic evidence supports this interpretation in ways that should make every historian reconsider their assumptions about cultural development. When researchers trace the etymological roots of technical and scientific terms across different ancient languages, they discover unexpected connections between cultures that supposedly developed in complete isolation from each other. Mathematical concepts, astronomical terminology, and engineering vocabulary show remarkable similarities across civilizations, separated by thousands of miles and hundreds of years. The probability of such linguistic parallels emerging independently is so small as to be essentially impossible. What we're seeing looks like fragments of a common technical vocabulary that was scattered across different survivor populations and gradually incorporated into their developing languages. But perhaps the most compelling evidence comes from the survivors' apparent obsession with creating redundant information storage systems. Early post-catastrophe civilizations didn't just build one monument encoding astronomical knowledge. They built dozens. They didn't just preserve mathematical relationships in a single location. They encoded the same information across multiple sites in different forms using various symbolic systems. This redundancy suggests a deep understanding of how catastrophic events can erase information. The builders had learned from bitter experience that single repositories of knowledge could be destroyed, that individual cultural traditions could be lost, that entire civilizations could disappear. Their response was to create multiple backup systems, encoding essential information in as many permanent forms as possible. The global distribution of these redundant information systems reveals something extraordinary about the scope of the recovery effort. Survivor populations separated by vast distances were apparently coordinating their monument-building activities, ensuring that critical knowledge would be preserved even if individual regions were struck by local disasters. This coordination required sophisticated communication networks spanning continents. It suggests organizational capabilities that go far beyond what we typically attribute to early post-catastrophe societies. These weren't isolated tribes struggling for basic survival. They were participating in a planet-wide effort to preserve and transmit essential knowledge across potential future catastrophes. The sheer scale of resources dedicated to these information preservation projects is staggering. Entire civilizations apparently organize their economies around the construction of permanent knowledge storage systems. Thousands of workers, decades of effort, massive resource allocation, all dedicated to ensuring that critical information would survive future disasters. This represents a fundamentally different approach to civilization building than what we see in our modern world. Instead of focusing primarily on immediate comfort, economic growth, or technological advancement, these societies prioritized long-term information preservation above almost everything else. They were building not just for their own generation, but for unknown future civilizations that might emerge after the next inevitable catastrophe. The mathematical precision of these monuments suggests they were designed by people who understood that future decoder would need exact measurements to reconstruct the encoded information. Slight variations in dimensions, small errors in alignment, minor imprecisions in construction. Any of these could render the encoded knowledge unreadable to future generations. The builders couldn't rely on written instructions or verbal traditions to explain their monuments to future archaeologists. Everything had to be encoded in the structures themselves, using mathematical relationships and astronomical alignments that would remain constant across millennia. The precision required for such encoding represents a level of planning and execution that challenges our understanding of prehistoric capabilities. Recent computer modeling of ancient monuments reveals just how sophisticated this encoding actually was. When researchers input the precise dimensions and alignments of structures like Göbekli Tepe or the stone circles of Britain into mathematical analysis programs, they discover layer upon layer of encoded information. Basic geometric relationships reveal astronomical cycles. More complex mathematical analysis uncovers engineering principles. Advanced computational techniques expose what appear to be sophisticated data compression systems, allowing enormous amounts of information to be encoded in relatively simple structural relationships. These weren't primitive religious monuments built by superstitious peoples trying to appease imaginary gods. They were sophisticated information storage systems created by scientifically advanced survivors who understood exactly what knowledge needed to be preserved and how to encode it in permanent, decodable form. The implications extend far beyond archaeology. If advanced civilizations have risen and fallen multiple times in human history, if planetary catastrophes periodically reset technological development, then we need to fundamentally reconsider our assumptions about progress, development, and the long-term trajectory of human civilization. We tend to think of technological advancement as a one-way process. Each generation builds upon the achievements of the previous one, creating an ever-upward climb toward greater sophistication and capability. But the Younger Dryas evidence suggests that progress might actually be cyclical, with periods of advancement followed by catastrophic setbacks that force survivors to rebuild from fragments. This cyclical model would explain many of the anomalies that have puzzled researchers for generations. The sudden appearance of sophisticated knowledge in the archaeological record, the remarkable similarities between supposedly unconnected ancient cultures, the apparent gaps and discontinuities in technological development, the persistent flood narratives found in cultures around the world. If human civilization has been through multiple cycles of advancement and catastrophic collapse, then our current technological society might not be humanity's first attempt at reaching advanced capabilities. We might be building upon foundations laid by previous civilizations whose achievements have been largely erased from the geological record. This possibility should profoundly change how we think about our relationship with the planet and our responsibilities to future generations. If catastrophic resets are periodic rather than random, if advanced civilizations are inherently vulnerable to planetary forces beyond their control, then we need to start planning for the preservation of essential knowledge across potential future disasters. The monument builders of the post-Younger Dryas period understood something that we're only beginning to grasp: that technological civilizations are far more fragile than they appear, and that preserving knowledge across catastrophic discontinuities requires deliberate, long-term planning that transcends individual lifetimes or political systems. Their solution was to encode essential information in permanent physical form using mathematical relationships that would remain constant regardless of cultural changes or technological setbacks. They created information storage systems designed to survive floods, earthquakes, climate changes, and societal collapses. But they also understood something else that we've largely forgotten: the importance of creating multiple redundant systems spread across different geographical regions. They didn't just preserve knowledge in one location or one format. They created dozens of backup systems, ensuring that critical information would survive even if most storage sites were destroyed. This redundancy principle has profound implications for how we should think about preserving our own civilization's achievements. Our current information storage systems are remarkably centralized and vulnerable. Digital networks can be disrupted by electromagnetic pulses. Computer systems can be destroyed by natural disasters. Even our physical libraries and archives are concentrated in urban areas that would be particularly vulnerable to catastrophic events. The ancient monument builders took a different approach. They distributed their information storage systems across continents, encoded knowledge in multiple formats, and used techniques designed construction to survive virtually any conceivable disaster. Their monuments have already survived over 12,000 years of climate changes, earthquakes, and human conflicts. With proper maintenance, they could potentially preserve information across multiple future catastrophic cycles. As we continue to decode the messages left behind by these ancient knowledge preservers, we're not just learning about the past. We're potentially discovering strategies that could help our own civilization survive future catastrophic events and transmit its achievements across the vast timescales on which planetary disasters occur. The story of the Younger Dryas catastrophe and its aftermath isn't just ancient history. It's a case study in civilizational resilience, a guide to the challenges that technologically advanced societies face when confronted with planetary forces beyond their control. The survivors who built the information preservation monuments weren't just trying to rebuild their own world future civilizations avoid. They were trying to help repeating the same catastrophic cycle. Their message, encoded in stone and mathematics, is both a warning and an instruction manual. A warning about the fragility of technological civilization and the reality of cyclical catastrophes. An instruction manual for preserving essential knowledge across the gaps in continuity that such events inevitably create. The question that confronts us now is whether we're wise enough to understand their message and act upon its implications before we're forced to learn the same lessons through our own experience with planetary catastrophe. The evidence suggests that we may not have as much time as we think to figure out these answers. The evidence becomes even more unsettling when we examine what researchers are calling the knowledge cascade phenomenon. Picture walking through a library where every book has had random chapters ripped out, pages scattered to the wind, but somehow the most critical information has been carefully preserved in code. That's essentially what we're seeing in the archaeological record following the Younger Dryas catastrophe. Here's something that should make every scientist pause and reconsider our timeline. The survivors didn't just randomly preserve bits and pieces of their former civilization's knowledge. They made strategic choices about what to save, what to encode in permanent form, and what to transmit to future generations. This wasn't the desperate scavenging of confused refugees. This was a systematic preservation effort undertaken by people who understood exactly what knowledge was most critical for rebuilding technological civilization. Think about it this way. If our modern world suddenly collapsed tomorrow, what would you choose to preserve? Not your smartphone or your car. Those would be useless without the industrial infrastructure to support them. You'd focus on fundamental principles, mathematics, physics, agricultural techniques, basic engineering, astronomical knowledge for navigation and timekeeping, medical understanding, the core knowledge that would allow survivors to eventually rebuild technological capability from the ground up. This is exactly what we see encoded in post-Younger Dryas monuments. Not random decorative elements or primitive religious symbolism, but systematic preservation of precisely the knowledge that would be most essential for civilizational recovery. The builders weren't creating art. They were building textbooks in stone. But here's where this gets really mind-bending. Recent analysis of these monuments reveals that they contain far more information than we initially realized. We're not just talking about basic astronomical alignments or simple geometric relationships. We're looking at compressed data storage systems that encode multiple layers of information in single structural elements. Consider the mathematical elegance of this approach. A single stone circle can simultaneously function as a calendar, a surveying instrument, a mathematical teaching tool, and an astronomical observatory. The same structural relationships that allow you to predict eclipses also encode the mathematical constants needed for advanced engineering. The geometric proportions that create optimal acoustic effects also preserve the ratios necessary for precision construction techniques. This represents a level of information compression that we've only recently learned to achieve with computer algorithms. The ancient builders were essentially creating analog computers carved in stone, capable of performing complex calculations and preserving vast amounts of data in compact, permanent form. The sophistication of these systems becomes even more apparent when we examine how they were designed to remain functional across multiple centuries of cultural change. The builders couldn't assume that future users would speak their language, understand their symbols, or share their cultural references. Everything had to be encoded using universal mathematical relationships that would remain constant regardless of cultural evolution, but they also had to account for potential changes in astronomical conditions. The positions of stars shift over time due to precession. The length of the year changes due to orbital variations. Even the fundamental constants of mathematics remain stable, but their practical applications might be affected by technological changes or environmental shifts. The monument builders solved this problem by creating what we can only describe as self-electing information core systems. Their structures encode not just specific data, but the methodologies needed to update and recalibrate that data as conditions change. They built in error correction protocols, redundant verification systems, and adaptive algorithms that would allow future users to maintain accuracy even as underlying conditions shifted. This level of systematic thinking suggests organizational capabilities that go far beyond anything we typically attribute to prehistoric societies. We're looking at evidence of large-scale collaborative projects involving multiple generations of builders, all working according to consistent design principles and shared technical standards. The coordination required for such projects is staggering. Different construction teams working at different sites had to maintain precise mathematical relationships between their monuments. Astronomical alignments had to be calculated not just for individual locations, but for the entire network of sites working together as an integrated information system. This network approach reveals something extraordinary about the scope of the post-catastrophe recovery effort. Survivor populations weren't just rebuilding their local communities, they were participating in a continent-spanning project to preserve and transmit essential knowledge. The monuments we see scattered across different regions weren't isolated local initiatives. They were components of a coordinated global information preservation system. Recent satellite mapping has revealed the true extent of this network. When you plot the locations of major post-Younger Dryas monuments on a global map, patterns emerge that are difficult to explain as coincidence. The distances between sites follow specific mathematical relationships. The alignments connect monuments separated by thousands of miles. The overall distribution suggests a master plan implemented across multiple continents. But here's what really should keep you awake at night. The mathematical relationships encoded in these monuments aren't just random formulas or abstract concepts. They're practical engineering specifications, blueprints for technologies, instruction manuals for reconstructing advanced capabilities. Take metallurgy, for instance. The geometric proportions found in certain stone circles correspond exactly to the ratios needed for optimal furnace design. The angles and measurements encode information about temperature control, alloy composition, and heat treatment processes. Someone familiar with metalworking could theoretically use these monuments as guides for reconstructing sophisticated metallurgical techniques. The same principle applies to other technologies. Agricultural knowledge is encoded in seasonal alignments and planting calendars. Navigation techniques are preserved in stellar maps and coordinate systems. Even what appears to be medical knowledge can be found in certain acoustic properties and geometric relationships that correspond to known healing frequencies. This suggests that the monument builders weren't just preserving abstract scientific knowledge, they were creating practical instruction manuals for rebuilding technological civilization. The monuments function as distributed technical libraries, each one containing pieces of a larger technological puzzle that could theoretically be reassembled by sufficiently advanced future civilizations. But there's a darker implication here. If these monuments were designed as recovery manuals for future catastrophe survivors, it means their builders expected the cycle to repeat. They weren't just preserving knowledge as a historical curiosity, they were preparing for the next inevitable collapse. This expectation is built into the very structure of their information preservation systems. The monuments aren't just designed to survive normal weathering and erosion, they're engineered to withstand catastrophic events, massive stone blocks that could survive earthquakes, foundations designed to remain stable even if surrounding soil shifts dramatically, construction techniques that could maintain structural integrity even if the local climate changes completely. The builders were planning for scenarios that go far beyond normal historical discontinuity. They were preparing for events that could fundamentally alter the planetary environment, shift continents, change sea levels, and disrupt the basic conditions that support human civilization. This level of catastrophic planning suggests they had direct experience with such events. The monument builders weren't working from theoretical models or abstract fears. They were responding to lived trauma. They had witnessed the complete destruction of an advanced civilization and were determined to ensure that essential knowledge would survive the next such event. The psychological implications of this realization are staggering. Imagine living with the knowledge that your entire world could disappear virtually overnight, that all of your achievements, all of your accumulated progress, all of the foundations of your society could be swept away by forces completely beyond your control. This trauma would fundamentally shape every aspect of how you approach civilization building. You wouldn't just build for comfort or convenience, you'd build for survival across catastrophic discontinuities. You wouldn't just pursue knowledge for its own sake, you'd focus on preserving and transmitting the specific information that would be most critical for recovery efforts. This mindset explains another puzzling aspect of post-Younger Dryas archaeology: the apparent reluctance to rebuild coastal settlements. Even though sea levels had stabilized and coastal areas offered obvious advantages for trade and transportation, early civilizations consistently chose inland locations for their major centers. This wasn't just practical caution based on recent flooding. It represents a fundamental shift in how these societies thought about geographical risk. They had learned that coastal areas, no matter how advantageous, were inherently vulnerable to catastrophic sea level changes. Their settlement patterns reflect deep cultural memories of watching entire civilizations disappear beneath rising waters. But they also understood something else that we're only beginning to appreciate: the importance of geographical diversity in information preservation. By distributing their monuments across different climate zones, geological formations, and elevation levels, they ensured that at least some of their information storage systems would survive even massive environmental changes. This distributed approach created remarkable redundancy in their knowledge preservation systems. The same essential information was encoded in monuments built in deserts, mountains, river valleys, and highland plateaus. Even if catastrophic events destroyed most of these sites, enough would survive to allow future civilizations to reconstruct the preserved knowledge. The builders also understood the importance of using locally available materials and construction techniques that could be maintained by future populations with limited technological capabilities. They didn't rely on exotic materials or complex manufacturing processes that might not be available to catastrophe survivors. Instead, they used basic stone and earth construction techniques that could be understood and maintained by relatively simple societies. This practical approach to monument design reveals sophisticated thinking about the long-term maintenance requirements of information storage systems. The builders weren't just creating monuments that would physically survive catastrophic events. They were ensuring that future populations would have the knowledge and resources necessary to maintain and decode these systems. But perhaps the most remarkable aspect of their approach was the creation of what researchers are calling bootstrap protocols, information sequences designed to help catastrophe survivors gradually reconstruct advanced technological capabilities. These aren't just random collections of useful knowledge. They're carefully structured learning progressions that build from basic principles to increasingly sophisticated applications. The monuments appear to be designed as educational systems that could guide recovering civilizations through the process of technological development, starting with fundamental mathematical and scientific principles, then progressing through basic engineering and manufacturing techniques, and eventually leading to more advanced applications that could support complex technological capabilities. This educational approach explains another mysterious aspect of post-catastrophe archaeology: the apparent speed with which certain civilizations develop sophisticated capabilities. They weren't starting from zero and learning everything through trial and error. They were following structured learning paths encoded in their monuments, allowing them to rapidly advance through technological development stages that might otherwise take centuries to achieve. The implications of this discovery extend far beyond archaeology and ancient history. If the monument builders succeeded in creating effective information preservation and transmission systems, it means that recovery from catastrophic collapse is not only possible, but can be significantly accelerated through proper preparation. This realization should fundamentally change how we think about long-term planning for our own civilization. Instead of assuming that technological progress is inevitably linear and cumulative, we should consider the possibility that periodic catastrophic resets are normal features of planetary development, and that advanced civilizations need to plan for these contingencies. The monument builders understood something that we've largely forgotten: that the true test of a civilization's advancement isn't how sophisticated its technologies become, but how effectively it can preserve and transmit its achievements across catastrophic discontinuities. They built not just for their own time, but for the unknown future civilizations that would inherit the fragments of their world. Their message, encoded in stone and mathematics across multiple continents, represents humanity's first systematic attempt to break the cycle of catastrophic civilizational collapse. Whether they succeeded remains to be seen. We may be living proof of their success, or we may be repeating the same cycle they hoped to end. The evidence suggests that we're approaching another potential inflection point in this ancient cycle. Climate instability, technological complexity, resource depletion, and social fragmentation, all of the conditions that preceded previous catastrophic collapses, are present in our modern world. The question is whether we'll be wise enough to learn from the monument builders' example before we're forced to repeat their experience. Their legacy offers both warning and hope. Warning about the fragility of technological civilization and the reality of periodic catastrophic resets. Hope that proper preparation can not only ensure survival across such events, but can significantly accelerate recovery efforts. The choice of how to respond to this knowledge may be the most important decision our species has ever faced. We can continue to assume that progress is inevitable and permanent, building ever more complex and fragile systems without considering long-term resilience. Or we can follow the example of the monument builders and begin creating our own information preservation systems designed to survive catastrophic events and guide future recovery efforts. The evidence from the Younger Dryas catastrophe suggests that we may not have as much time as we think to make this choice. The patterns encoded in ancient monuments point to cyclical processes that operate on timescales longer than individual civilizations, but shorter than species evolution. If these patterns hold true, then the next catastrophic reset may be closer than we imagine. The monument builders left us more than just archaeological mysteries to puzzle over. They left us a survival guide, written in stone and mathematics, designed to help future civilizations navigate the challenges they themselves had faced. Whether we're wise enough to read and understand their message may determine not just our own fate, but the fate of all future human civilizations that might emerge from whatever comes next. The scope of what we're discovering beneath the waves becomes more staggering with each passing expedition. When marine archaeologists first began systematically mapping the drowned landscapes of the continental shelves, they expected to find evidence of simple hunter-gatherer camps, maybe some basic fishing settlements. What they've uncovered instead challenges every assumption we've made about the capabilities of Ice Age civilizations. Picture this. You're piloting a deep-sea submersible across what was once a fertile river valley, now lying 400 feet beneath the Atlantic. Your lights illuminate structures that shouldn't exist, perfectly circular formations spanning hundreds of meters, stone arrangements that follow mathematical principles, artificial channels that once diverted rivers according to sophisticated hydraulic engineering principles. This isn't happening in just one location. Similar discoveries are emerging from drowned landscapes around the globe. Off the coast of India, researchers have mapped what appear to be the remains of massive port facilities, complete with breakwaters and artificial harbours that could have accommodated large vessels. Near Japan, underwater surveys have revealed stepped pyramidal structures with geometric precision that defies explanation through natural geological processes. But here's what should really grab your attention. These underwater sites aren't randomly scattered across the ocean floor like you'd expect from isolated settlements. They follow patterns. They're connected by what appear to be ancient roadways and canal systems, now buried under centuries of marine sediment. We're looking at the remnants of integrated infrastructure networks that once spanned entire continental shelves. The engineering sophistication required for such projects is breathtaking. These weren't simple coastal villages that happened to get flooded. We're talking about major population centres with advanced transportation networks, sophisticated water management systems, and construction techniques that demonstrate mastery of large-scale civil engineering. Consider what it means to build permanent infrastructure on continental shelf areas during the Ice Age. These regions would have been hundreds of kilometres from the nearest ocean, connected to inland areas by river systems that are now completely submerged. The builders would have needed to understand long-term geological stability, predict seasonal flooding patterns, and design drainage systems capable of handling massive water volumes. But they also would have needed something else that we rarely consider when thinking about prehistoric societies. They would have needed population density sufficient to justify such massive infrastructure investments. You don't build harbour facilities and transportation networks for small nomadic groups. These are the kinds of projects that require thousands of workers, sustained resource allocation, and centralised planning capabilities. Recent computer modelling of Ice Age sea levels has revealed just how much habitable land was lost when the great ice sheets melted. We're not talking about narrow coastal strips or small islands. The exposed continental shelves represented land masses comparable in size to entire modern countries. The Doggerland area that once connected Britain to continental Europe was larger than England. The Beringia land bridge between Asia and North America covered an area equivalent to several US states. But the most significant loss may have been the vast plain that once extended from what is now the eastern seaboard of North America far out into the Atlantic. This area, now lying under hundreds of feet of water, would have been prime real estate during the Ice Age. Fertile river valleys, protected harbours, strategic locations for trade and transportation. If advanced civilizations did develop in these areas, their destruction would have been absolute. When the ice sheets began collapsing and massive volumes of meltwater poured into the oceans, these low-lying coastal plains would have been the first casualties. The very features that made them attractive for settlement, river deltas, protected bays, fertile floodplains, would have become death traps as the waters rose. The speed of this inundation is crucial to understanding why so little evidence survives above water. Geological data suggests that some periods of sea level rise during the Younger Dryas melt occurred at rates measured in meters per century. That might sound gradual, but it means that coastal settlements would have been abandoned within single human lifetimes. Imagine generations of people watching their ancestral lands disappear beneath advancing waters. First, the outer settlements would be abandoned. Then the port facilities would be swallowed. Eventually, even the highest ground in these coastal areas would become uninhabitable as the waters continued their relentless advance. The psychological trauma of such an experience would have been beyond our ability to comprehend. These weren't just homes being lost. Entire ways of life were disappearing. Maritime trading networks that had operated for millennia would have been severed. Coastal cities that had served as centers of learning and culture would have been abandoned to the waves. But here's what makes this story even more compelling. The survivors of this catastrophe didn't just retreat inland and give up. They carried with them fragments of their maritime civilization's knowledge and began the long process of rebuilding in new environments. And the evidence suggests they were remarkably successful at preserving essential information across this transition. Think about the sudden appearance of advanced nautical knowledge in civilizations that supposedly developed far from oceanic influences. Ancient Egyptian texts describe sophisticated sailing vessels and navigation techniques. Mesopotamian records detail knowledge of tides, currents, and seasonal wind patterns. Even landlocked civilizations show understanding of maritime cycles that they shouldn't have possessed if they truly developed in isolation from oceanic cultures. What if this knowledge wasn't developed independently inland by these civilizations? What if it was inherited from refugees who had once been part of sophisticated maritime societies? The navigational techniques, the understanding of celestial navigation, the knowledge of shipbuilding and harbour construction. All of this could have been preserved and transmitted by survivors from the drowned coastal civilizations. This interpretation would explain one of archaeology's most persistent puzzles. Why do early civilizations demonstrate such sophisticated understanding of complex systems right from their earliest appearance in the historical record? Instead of showing gradual development of knowledge through trial and error, they seem to begin with comprehensive understanding already in place. The answer may be that they weren't starting from scratch. They were building upon inherited knowledge, adapting techniques developed by their maritime predecessors to new inland environments. The priests and scholars of early civilizations weren't discovering new principles. They were preserving and applying ancient wisdom that had been salvaged from the drowning world. Recent advances in underwater archaeology are beginning to reveal the true scope of what was lost. New sonar technologies can penetrate deep into marine sediments, revealing buried structures that have been hidden for millennia. Robotic submersibles can explore areas that were previously inaccessible to human investigators. And computer analysis of underwater formations can distinguish between natural geological features and artificial constructions with unprecedented accuracy. What these technologies are revealing is staggering. Massive stone constructions lying beneath hundreds of feet of sediment, geometric patterns that extend for miles across the ocean floor, artificial modifications to natural underwater features that demonstrate sophisticated understanding of hydraulic engineering. But perhaps most intriguingly, these discoveries are revealing evidence of what appears to have been systematic preparation for the coming catastrophe. Some underwater sites show signs of having been deliberately modified in ways that suggest their builders knew the waters were rising and were attempting to adapt their infrastructure to changing conditions. We're finding evidence of raised platforms, elevated roadways, and drainage systems that appear to have been constructed as responses to gradually rising water levels. These weren't random modifications or normal maintenance projects. They represent coordinated efforts to adapt existing infrastructure to changing environmental conditions. This suggests that the final generations of the maritime civilization were acutely aware of the threat they faced. They weren't caught completely off guard by rising sea levels. They were actively trying to engineer solutions to a problem they could see developing around them. But ultimately, their efforts weren't enough. The scale of the sea level rise was simply too massive for even sophisticated engineering to overcome. No matter how high they built their platforms or how complex they made their drainage systems, the relentless advance of the waters eventually overwhelmed their defenses. The archaeological evidence suggests that the final abandonment of these sites wasn't gradual or voluntary. We're finding signs of hasty evacuation, valuable materials left behind, and construction projects abandoned in mid-completion. This wasn't an orderly retreat. This was a desperate flight from rising waters that had finally exceeded all attempts at technological solutions. But the refugees who fled these drowning cities didn't just disappear into history. They became the founders of the inland civilizations that we recognize as the beginning of recorded history. They brought with them not just practical knowledge, but also cultural memories of their lost world that would influence human civilization for millennia to come. The flood narratives found in cultures around the globe aren't just mythological stories passed down through oral tradition. They're historical accounts of real events, preserved by people who had witnessed the destruction of an entire way of life. The details embedded in these stories, the descriptions of rising waters, the accounts of desperate evacuation, the memories of lost cities, these correspond remarkably well with what we're discovering through underwater archaeology. Consider the biblical account of Noah's flood, but read it not as divine testimony punishment, but as historical. A great deluge that covered the highest mountains, destroying all traces of the previous world, leaving only scattered survivors to rebuild civilization from fragments. This isn't mythology. This is eyewitness testimony, preserved across thousands of years of cultural transmission. The same pattern appears in flood narratives from cultures that had no contact with biblical tradition. Hindu accounts of cosmic deluges that reset the world. Native American stories of great waters that swallowed the land. Aboriginal Australian tales of rising seas that claimed ancestral territories. These aren't independent mythologies that happen to develop similar themes. They're cultural memories of the same catastrophic events. But these stories preserve more than just accounts of destruction. They also contain detailed information about survival strategies, technological knowledge, and cultural practices that would be essential for rebuilding civilization after catastrophic collapse. The flood narratives aren't just historical records, they're instruction manuals for catastrophe survival. This brings us to a profound realization about the nature of human cultural transmission. The stories we dismiss as primitive mythology may actually represent some of our species' most important historical documents. Encoded within these narratives are not just accounts of past catastrophes, but practical guidance for surviving future ones. The maritime civilization that was destroyed during the Younger Dryas flooding left us more than just archaeological mysteries buried beneath the waves. They left us a cultural inheritance preserved in the flood stories that have shaped human consciousness for millennia. These stories aren't just entertainment or religious instruction. They're survival guides written by people who had experienced civilizational collapse and wanted to help their descendants avoid repeating the same tragic cycle. As we continue to explore the drowned landscapes of the continental shelves, we're not just uncovering evidence of lost cities and forgotten technologies. We're discovering the origins of humanity's oldest and most persistent cultural memories. The stories that have shaped our understanding of catastrophe, survival, and renewal aren't mythological fantasies. They're historical accounts of our species' greatest trial and most remarkable recovery. The implications extend far beyond archaeology and ancient history. If advanced maritime civilizations have risen and fallen before, if catastrophic sea level changes are periodic features of planetary development rather than unique historical events, then we need to seriously consider what this means for our own coastal civilizations. Today, the majority of human population and infrastructure is concentrated in exactly the same kinds of locations that were destroyed during the Younger Dryas catastrophe. Coastal cities, river deltas, low-lying plains near major water bodies. If similar catastrophic sea level changes were to occur again, the impact on modern civilization would be absolutely devastating. But the story of the Younger Dryas survivors also offers hope. It demonstrates that even complete civilizational collapse doesn't necessarily mean the end of human progress. Knowledge can be preserved across catastrophic discontinuities. Technologies can be rebuilt from fragments. Civilizations can rise again from the scattered remnants of what came before. The question is whether we'll be wise enough to learn from their example before we're forced to repeat their experience. The survivors of the maritime catastrophe left us a blueprint for preservation and recovery, encoded in monuments, cultural traditions, and flood narratives that have endured for over 12,000 years. Their message is both a warning and an instruction manual. A warning about the fragility of coastal civilizations and the reality of periodic catastrophic changes. An instruction manual for preserving essential knowledge and capabilities across the gaps in continuity that such events inevitably create. The evidence suggests that we may be approaching another potential inflection point in this ancient cycle. Climate change, rising sea levels, increasing geological instability. All of the conditions that preceded the Younger Dryas catastrophe are present in our modern world. The question is whether we'll heed the warnings preserved in our oldest cultural memories and begin preparing for the challenges that may lie ahead. The drowned cities lying beneath the waves aren't just archaeological curiosities. They're previews of what could happen to our own coastal civilizations if we fail to understand the lessons they're trying to teach us. But they're also proof that recovery is possible, that human ingenuity and resilience can survive even the most catastrophic setbacks, and that knowledge properly preserved can bridge the gaps between the rise and fall of civilizations. The story of the Younger Dryas catastrophe isn't just ancient history, it's a case study in planetary catastrophe and human survival, a guide to the challenges that coastal civilizations face when confronted with forces beyond their control. The survivors who rebuilt civilization from the fragments of the drowned world weren't just trying to restore what they had lost. They were trying to ensure that future generations would be better prepared for the inevitable next cycle. Their legacy challenges us to think beyond the immediate concerns of our current civilization and consider the long-term patterns that shape human development on geological timescales. If we're wise enough to understand their message and act upon its implications, we might finally break the cycle of catastrophic collapse and recovery that has defined human civilization since the Great Drowning began. The answers to our future may lie buried beneath the waves, waiting for us to develop the technology and wisdom necessary to decode the messages left behind by those who face the ultimate test of civilizational survival and somehow manage to pass their knowledge forward to us. The technological capabilities we're beginning to understand about this lost civilization reach levels that should fundamentally challenge our assumptions about prehistoric human development. We're not just talking about impressive stonework or basic astronomical knowledge anymore. Recent discoveries are revealing evidence of manufacturing precision, metallurgical sophistication, and engineering capabilities that rival modern industrial processes. Let's examine something that should make every materials scientist reconsider our timeline. Stone artifacts recovered from sites dating immediately after the Younger Dryas period show machining marks that are virtually impossible to explain using conventional archaeological theories. We're talking about surface finishes that are smooth to within microscopic tolerances, drill holes that maintain perfect cylindrical geometry through the hardest granite, and cutting edges that demonstrate understanding of crystalline structure at the molecular level. But here's what makes this truly extraordinary. These aren't isolated examples found at one or two exceptional sites. This level of precision appears across multiple continents, in artifacts created by supposedly unconnected cultures that had no contact with each other. The mathematical accuracy, the consistency of techniques, the sophisticated understanding of material properties. It all points to inherited knowledge rather than independent discovery. Consider what would be required to achieve such precision using the tools that mainstream archaeology attributes to these periods. Try to imagine creating perfectly circular holes through solid granite using copper tools and sand abrasives. Attempt to visualize polishing stone surfaces to mirror-like finishes using only primitive grinding techniques. The amount of time, effort, and technical expertise required would be staggering, if it's even possible at all. Yet the evidence is undeniable. Objects that display machining precision comparable to modern industrial equipment. Surfaces that show tool marks consistent with high-speed rotary cutting implements. Construction techniques that demonstrate understanding of stress analysis, load distribution, and structural engineering principles that supposedly weren't developed until the modern era. The metallurgical evidence is equally compelling. Artifacts from this period show understanding of alloy compositions that require precise temperature control and sophisticated smelting techniques. We're finding evidence of metals that have been work-hardened using techniques that weren't supposedly rediscovered until the Industrial Revolution. Some artifacts show signs of having been created using casting methods that require advanced understanding of thermal expansion, cooling rates, and mold design. But perhaps most intriguingly, we're discovering evidence of what appears to be electrochemical processing. Certain metal objects show surface treatments that are difficult to explain without assuming knowledge of electrical phenomena. Uniform coating thicknesses, selective plating of specific areas, and corrosion resistance that suggests understanding of galvanic processes. This raises profound questions about the level of scientific knowledge possessed by post-catastrophe civilizations. If they inherited understanding of electrical phenomena from their maritime predecessors, it would explain many anomalies in the archaeological record. The precision of their metalworking, the sophistication of their surface treatments, even the acoustic properties of their monuments could be explained by access to electrochemical techniques. Recent analysis of ancient monuments has revealed another layer of sophistication that challenges our understanding of prehistoric capabilities. Many of these structures demonstrate understanding of resonant frequencies and harmonic relationships that would require advanced knowledge of physics and mathematics to calculate and implement. We're not talking about accidental acoustic effects that happen to emerge from random construction choices. These are precisely engineered sound systems, designed to produce specific frequencies and acoustic environments. The mathematical relationships between chamber dimensions, the careful placement of resonating surfaces, the strategic use of different stone types to create desired tonal qualities. This represents a level of acoustic engineering that we've only recently learned to achieve using computer modeling and advanced materials science. What makes this even more remarkable is the consistency of certain frequencies across monuments built in different locations and time periods. Specific resonant frequencies appear again and again in structures separated by thousands of miles and hundreds of years. This suggests not random experimentation, but systematic application of established acoustic principles. The potential purposes of these acoustic systems are fascinating to consider. Modern research into sound frequencies and their effects on human consciousness has revealed that certain vibrations can induce altered states of awareness, promote healing responses, and even affect cognitive function. If the monument builders understood these principles, it would indicate knowledge of human neuroscience and physiology that supposedly wasn't developed until the modern medical era. But the acoustic engineering represents just one aspect of a much larger pattern of technological sophistication. When we examine the full range of capabilities demonstrated by post-catastrophe civilizations, we're looking at knowledge systems that appear to have been inherited rather than developed through gradual experimentation. Take their understanding of astronomy, for instance. The precision of celestial observations encoded in ancient monuments requires not just careful watching of the skies, but sophisticated mathematical analysis of complex cycles and relationships. The builders weren't just tracking the obvious movements of sun and moon. They were calculating precession, predicting eclipses centuries in advance, and encoding knowledge of stellar positions with accuracy that matches modern telescopic observations. This level of astronomical precision demands advanced measuring instruments. You simply cannot track celestial movements to the accuracy we see in these monuments using naked eye observation alone. The calculations would require understanding of atmospheric refraction, mathematical correction for observational errors, and long-term data collection using standardized measurement techniques. Yet somehow, builders working with supposedly primitive tools achieved measurement accuracy that rivals modern astronomical equipment. They created observatories that function as precision instruments, capable of detecting and measuring celestial phenomena that are barely visible without advanced technology. The mathematical knowledge embedded in these constructions is equally sophisticated. We're finding evidence of understanding of advanced geometric principles, complex numerical relationships, and mathematical constants that supposedly weren't discovered until much later in human history. The golden ratio appears in monuments built by cultures that had no supposed contact with Greek mathematics. Pi is encoded in structures that predate its supposed discovery by centuries. But it's not just the presence of these mathematical relationships that's remarkable. It's the sophisticated way they're integrated into functional architectural systems. The same geometric proportions that create aesthetically pleasing visual effects also optimize structural stability. The mathematical ratios that produce desired acoustic properties also encode astronomical calculations. The builders were creating multifunctional systems where advanced mathematics served multiple practical purposes simultaneously. This integration of mathematical principles into functional architecture suggests a level of systematic thinking that goes far beyond primitive trial-and-error construction methods. We're looking at evidence of comprehensive design methodologies that incorporated advanced knowledge from multiple scientific disciplines. Recent computer analysis of ancient construction techniques has revealed another make every engineer re-see layer of sophistication that should alongside our assumptions about prehistoric capabilities. Many monuments demonstrate understanding of load distribution, stress analysis, and structural dynamics that require advanced engineering knowledge to implement effectively. Consider the precision required to balance massive stone blocks in structures that have remained stable for thousands of years. The builders had to account not just for the weight of individual stones, but for how that weight would be distributed through complex three-dimensional structures. They had to calculate how thermal expansion and contraction would affect joints and connections. They had to design foundations capable of maintaining stability through earthquakes, floods, and dramatic climate changes. The engineering solutions they implemented are often more sophisticated than what we might choose using modern techniques. Their methods for moving and positioning massive stones demonstrate understanding of mechanical advantage, leverage, and force distribution that rivals modern heavy construction practices. Some of their techniques are so elegant and efficient that modern engineers are studying them to improve current construction methods. But perhaps most remarkably, they achieved all of this using construction materials that were locally available and techniques that could be maintained by relatively simple societies. They didn't rely on exotic materials or complex manufacturing processes that would become unavailable if supply chains were disrupted. Instead, they created sophisticated technological solutions using basic materials and techniques that could be understood and replicated by future generations with limited technological capabilities. This practical approach to advanced engineering reveals sophisticated thinking about long-term maintenance and technological sustainability. The builders weren't just creating impressive monuments, they were ensuring that their technological solutions would remain functional and maintainable across potential future catastrophes. The global distribution of these sophisticated techniques raises another profound question about the coordination of post-catastrophe recovery efforts. We're not looking at isolated examples of exceptional achievement by individual genius builders. We're seeing consistent application of advanced techniques across multiple continents, suggesting coordinated implementation of shared technological knowledge. This coordination would have required communication networks spanning vast distances. It implies organizational capabilities that go far beyond what we typically attribute to early post-catastrophe societies. These weren't isolated survivor groups struggling for basic subsistence. They were participating in organized, large-scale technological reconstruction efforts. The resource allocation required for such projects is staggering. Entire societies apparently reorganized their economies around the construction of sophisticated technological systems. Thousands of workers, specialized craftsmen, advanced materials, precise tools, all coordinated according to standardized technical specifications implemented across multiple regions. This represents a fundamentally different approach to post-catastrophe recovery than what we might expect from traumatized survivor populations. Instead of focusing primarily on immediate survival needs, these societies prioritized the reconstruction of advanced technological capabilities that would support long-term civilizational development. The speed with which these technological reconstruction efforts were implemented is equally remarkable. Within just a few centuries of the catastrophic flooding, sophisticated construction projects were underway across multiple continents. This wasn't gradual redevelopment over millennia. This was rapid, coordinated implementation of advanced technological systems. This rapid reconstruction suggests that the survivors possessed not just theoretical knowledge, but practical experience with large-scale technological implementation. They knew not just what to build, but how to organize the human and material resources necessary to build it effectively. This represents institutional knowledge that goes far beyond individual technical skills. But here's what should really keep researchers awake at night. The technological capabilities we're discovering aren't just impressive achievements by prehistoric standards. Some of them appear to exceed what we can accomplish using modern techniques. The precision of certain stone cutting, the sophistication of acoustic engineering, the integration of multiple advanced systems into single architectural solutions. These represent technological approaches that we're still trying to understand and replicate. This raises uncomfortable questions about our assumptions regarding technological progress. We tend to think of advancement as inevitably linear, with each generation building upon the achievements of the previous one to create ever more sophisticated capabilities. But the evidence from post-Younger Dryas civilizations suggests that technological development might be more cyclical than linear. What if previous civilizations had achieved technological capabilities that were lost during catastrophic collapses, requiring subsequent societies to gradually rediscover and rebuild advanced systems from incomplete fragments? What if some of the sophisticated techniques we're discovering in ancient monuments represent knowledge that was inherited from even earlier civilizations that had achieved even greater technological heights? The implications extend beyond archaeology into fundamental questions about the nature of technological civilization itself. If advanced knowledge can be lost and recovered multiple times throughout history, it suggests that our current technological achievements might be more fragile and less permanent than we assume. The monument builders seem to have understood this fragility intimately. Their construction techniques, their information encoding systems, their approach to technological implementation. All of it reflects deep awareness that technological civilizations are vulnerable to catastrophic disruption, and that advanced knowledge must be preserved in forms that can survive across discontinuities in cultural transmission. This awareness shaped every aspect of their technological reconstruction efforts. They didn't just rebuild advanced capabilities. They rebuilt them in ways designed to survive future catastrophes. They created redundant systems, distributed technologies across multiple locations, and encoded essential knowledge in permanent forms that could be decoded by future civilizations with sufficient understanding. Their approach to technology represents a fundamentally different philosophy than what we see in our modern world. Instead of pursuing maximum sophistication and efficiency, they prioritized resilience, maintainability, and long-term survival. They built not just for their own generation, but for unknown future civilizations that might inherit the fragments of their achievements. This long-term thinking reveals profound wisdom about the challenges facing technological civilizations on geological timescales. The builders had learned through bitter experience that even the most advanced societies can be reduced to scattered survivors by planetary forces beyond their control. Their response was to create technological systems designed to bridge the gaps between civilizational collapse and recovery. As we continue to decode the sophisticated technologies preserved in ancient monuments, we're not just learning about impressive prehistoric achievements. We're discovering alternative approaches to technological development that prioritize long-term resilience over short-term advancement. We're uncovering strategies for preserving and transmitting advanced knowledge across catastrophic discontinuities. The lessons embedded in these ancient technological systems may be more relevant to our modern world than we realize. As our own civilization becomes increasingly complex and interconnected, it also becomes more vulnerable to catastrophic disruption. The technological philosophy demonstrated by post-Younger Dryas societies, emphasizing resilience, redundancy, and long-term survival, may offer crucial insights for building more robust and sustainable technological systems. The evidence suggests that the builders of these monuments understood something that we're only beginning to appreciate, that the ultimate test of any technological civilization isn't how advanced its capabilities become, but how effectively it can preserve and transmit its achievements across the inevitable catastrophic events that punctuate planetary development. Their technological legacy represents more than just impressive prehistoric engineering. It represents a comprehensive strategy for technological survival across geological timescales. Whether we're wise enough to understand and implement these strategies before facing our own potential catastrophic challenges may determine not just our fate, but the fate of all future technological civilizations that might emerge from whatever comes next. The sophisticated systems they created continue to function after 12,000 years of climate changes, geological upheavals, and human conflicts. With proper understanding and maintenance, they could potentially preserve essential technological knowledge across multiple future catastrophic cycles. The question is whether we'll develop the wisdom to decode and implement their preservation strategies before we're forced to learn the same lessons through our own experience with civilizational collapse. The mystery deepens when we examine what researchers are discovering about the survivors' mathematical encoding systems. These weren't simple astronomical alignments or basic geometric patterns. We're looking at sophisticated compression algorithms carved in stone, capable of storing vast amounts of information in remarkably compact forms. Picture walking into an ancient library where every book has been condensed into a single page, but somehow all the essential information remains perfectly preserved and accessible. That's essentially what these monument builders achieved with their encoding techniques. They developed methods for layering multiple data sets within single architectural elements, creating what can only be described as analog computers disguised as religious structures. The mathematical elegance of this approach becomes apparent when you realize that a single stone circle can simultaneously function as a calendar, a surveying instrument, a teaching tool for advanced mathematics, and a precision observatory for tracking celestial movements. The same geometric relationships that allow you to predict eclipses also encode the mathematical constants needed for engineering calculations. The proportions that create optimal acoustic effects also preserve the ratios necessary for metallurgical processes. This level of information compression represents a technological achievement that we've only recently learned to accomplish using digital systems. The ancient builders were essentially creating three-dimensional databases, storing multiple layers of technical knowledge in structural relationships that would remain stable and readable across millennia. But here's what should really capture your attention. These encoding systems weren't just designed to preserve information. They were designed to reveal that information gradually as the reader's understanding developed. The monuments function as progressive educational systems, revealing basic principles to novice observers while encoding advanced concepts that become apparent only to those with sufficient mathematical sophistication. Consider the implications of this approach. The builders couldn't assume that future users would possess the same level of technical knowledge as their own civilization. They had to create information systems that could serve both as basic educational tools for societies just beginning to redevelop scientific understanding, and as advanced technical references for civilizations that had progressed to higher levels of sophistication. This adaptive design philosophy reveals extraordinary foresight about the challenges of cross-generational knowledge transmission. The monument builders understood that catastrophic events don't just destroy infrastructure and population, they disrupt the continuity of educational systems that allow advanced knowledge to be passed from one generation to the next. Their solution was to create self-teaching systems that could guide recovering civilizations through the entire process of technological redevelopment. Starting with fundamental mathematical principles, clearly encoded in basic geometric relationships, then progressing through increasingly sophisticated applications that become accessible as the reader's understanding advances. Recent computer analysis of these encoding systems has revealed just how sophisticated this progressive revelation approach actually was. The monuments contain what researchers are calling knowledge trees, branching information structures where mastery of basic concepts unlocks access to more advanced material, which in turn reveals even more sophisticated applications. This hierarchical approach to information storage explains another puzzling aspect of post-catastrophe archaeological sites. Why do some locations show evidence of basic technological capabilities, while others in the same region demonstrate much more advanced applications? The answer may be that different communities had progressed to different levels in decoding the information preserved in their local monuments. Communities that had successfully decoded the basic levels of encoded information would have gained access to fundamental principles of mathematics, astronomy, and engineering. But those that progressed further through the knowledge trees would have unlocked increasingly sophisticated applications, advanced metallurgy, precision construction techniques, complex acoustic engineering. This creates a fascinating picture of post-catastrophe recovery as an educational process, with different survivor communities advancing at different rates based on their success in decoding the information preservation systems left behind by their predecessors. Some groups might remain at basic agricultural levels, while others in nearby regions developed sophisticated technological capabilities, all based on how effectively they could interpret the same underlying information systems. The global coordination required to implement such a system is staggering. Monument builders across different continents had to agree on consistent encoding protocols, mathematical standards, and progressive revelation sequences. This wasn't just a local preservation effort. This was a planet-wide educational project designed to guide the entire species through technological recovery. But the sophistication of these systems raises another profound question. If post-catastrophe civilizations could develop such advanced information preservation techniques, what level of knowledge must have been possessed by the original maritime civilization that was destroyed in the flooding? The encoding systems we're discovering may represent only the fragments that survivors could preserve from a much larger body of knowledge. Think about it this way. If our modern civilization were suddenly destroyed and only scattered survivors remained, they might be able to preserve some basic scientific principles, fundamental mathematical relationships, and essential engineering concepts. But the vast majority of our accumulated knowledge, our databases, our research libraries, our technical documentation, would be lost forever. The survivors would face the challenge of encoding whatever they could remember into permanent form, knowing that future generations would need to reconstruct the missing pieces through their own efforts. The monuments we're studying may represent exactly this kind of emergency preservation effort, the best that traumatized survivors could do to preserve fragments of their former civilization's knowledge. This interpretation would explain why the encoded information appears to be carefully selected rather than comprehensive. The monument builders weren't trying to preserve all knowledge. They were focusing on the specific information that would be most critical for technological recovery. Mathematical principles that could be applied to multiple engineering problems. Astronomical knowledge essential for navigation and timekeeping. Metallurgical techniques needed for tool production. Construction methods necessary for permanent architecture. Recent discoveries are revealing that this selective preservation approach extended beyond just technical knowledge into cultural and social information as well. Some monuments appear to encode not just scientific principles, but also organizational methods, social structures, and governance systems that would be necessary for coordinating large-scale reconstruction efforts. These cultural encoding systems are more subtle than the technical information, often embedded in symbolic representations and mythological narratives that require deeper interpretation to decode. But when properly understood, they reveal sophisticated understanding of social dynamics, resource management, and collaborative organization that would be essential for rebuilding complex civilizations. The flood narratives found in cultures around the world may represent one aspect of this cultural encoding system. These stories don't just preserve historical accounts of the catastrophe, they also contain practical guidance for surviving similar future events, instructions for recognizing the warning signs of impending disaster, techniques for preserving essential resources during catastrophic events, strategies for maintaining social cohesion among survivor populations. When viewed from this perspective, the global consistency of flood narratives takes on new significance. These aren't just similar stories that happen to develop independently. They're components of a coordinated information preservation system designed to ensure that future civilizations would be prepared for cyclical, catastrophic events. The practical implications of this realization are profound. If the monument builders succeeded in creating effective information preservation and cultural transmission systems, it means that recovery from civilizational collapse isn't just possible. It can be systematically accelerated through proper preparation and knowledge preservation. This understanding should fundamentally change how we think about our own civilization's vulnerability to catastrophic events. Instead of assuming that technological progress is inevitably cumulative and permanent, we should consider the possibility that periodic resets are normal features of planetary development and that advanced civilizations need to plan for these contingencies. The monument builders developed their sophisticated preservation systems because they had direct experience with civilizational collapse. They knew from bitter personal experience how quickly even the most advanced societies could be reduced to scattered refugees, carrying only fragments of their former knowledge. Their response was to create information systems designed not just for their own time, but for all future civilizations that might face similar challenges. They built redundant encoding systems, distributed preservation networks, and progressive educational structures that could guide recovering societies through the entire process of technological redevelopment. But they also understood something else that we're only beginning to appreciate: the importance of creating preservation systems that could survive not just physical destruction, but also the gradual erosion of knowledge that occurs when complex information systems aren't actively maintained by knowledgeable practitioners. Their solution was to embed essential information in the fundamental structure of their monuments, using mathematical relationships and physical proportions that would remain constant even if the cultural context for understanding them was temporarily lost. Future civilizations might forget the specific meaning of symbolic representations, but the mathematical constants encoded in geometric relationships would remain accessible to any society that redeveloped sufficient mathematical sophistication. This approach to information preservation reveals profound wisdom about the long-term challenges facing any technological civilization. The builders had learned that the greatest threat to knowledge isn't just catastrophic destruction, but the gradual loss of understanding that occurs when information systems become too complex or specialized to be maintained by reduced populations. Their monuments represent a different approach to knowledge preservation, one that prioritizes accessibility and self-revelation over comprehensive detail. Instead of trying to preserve every aspect of their former civilization's achievements, they focused on encoding the essential principles that would allow future societies to reconstruct advanced capabilities through their own efforts. Recent analysis suggests that this approach may have been remarkably successful. The rapid development of sophisticated capabilities by early historical civilizations, the sudden appearance of advanced knowledge in multiple fields, the consistent application of complex techniques across supposedly isolated cultures, all of this could be explained by successful decoding of information preserved in monument networks. If this interpretation is correct, then our own historical development may not represent humanity's first climb toward technological sophistication. Instead, we might be living through the results of a carefully planned recovery program, guided by information systems created by survivors of an earlier catastrophic collapse. This possibility has profound implications for how we understand human progress and our relationship with planetary forces. If advanced civilizations have risen and fallen multiple times throughout human history, it suggests that technological development follows cyclical patterns rather than linear progression. The monument builders seem to have understood these cycles intimately. Their preservation systems weren't just designed to help their immediate descendants. They were created to assist multiple future civilizations that might emerge and develop across recurring catastrophic cycles. This long-term perspective on civilizational development reveals a fundamentally different approach to progress than what characterizes our modern world. Instead of focusing primarily on advancing current capabilities, the monument builders prioritized creating systems that could preserve and transmit essential knowledge across multiple cycles of collapse and recovery. Their legacy offers both warning and instruction for our own civilization. Warning about the cyclical nature of catastrophic events and the vulnerability of even advanced technological societies. Instruction about methods for creating resilient information preservation systems that can maintain knowledge continuity across discontinuous events. As we continue to decode the sophisticated preservation systems created by these ancient knowledge guardians, we're not just learning about impressive prehistoric achievements. We're discovering strategies for technological survival that may be directly relevant to challenges facing our own civilization. The evidence suggests that we may be approaching another potential inflection point in the ancient cycle of advancement and collapse, The same kinds of environmental instabilities, resource pressures, and systemic vulnerabilities that preceded previous catastrophic resets are present in our modern world. The question that confronts us is whether we'll be wise enough to learn from the monument builders' example and begin creating our own information preservation systems before we're forced to repeat their experience with civilizational collapse. Their sophisticated encoding techniques, their distributed preservation networks, their progressive educational structures, all of these represent tested strategies for maintaining knowledge continuity across catastrophic discontinuities. The builders left us more than just archaeological puzzles to solve. They left us a comprehensive guide to civilizational resilience, encoded in stone and mathematics, designed to help future societies navigate the challenges they themselves had faced. Whether we're intelligent enough to decode and implement their guidance may determine not just our own fate, but the fate of all future human civilizations that might emerge from whatever challenges lie ahead. Their monuments continue to function as intended after 12 millennia of climate changes, geological upheavals, and cultural transformations. The information they preserved remains accessible to any civilization sophisticated enough to recognize and decode their encoding systems. The educational pathways they created still offer guided routes through technological redevelopment for societies beginning the recovery process. As we reach the end of this journey through time, we find ourselves staring at evidence that fundamentally challenges everything we thought we knew about human history. The Younger Dryas catastrophe wasn't just another climate event. It may have been the Great Reset that erased humanity's first technological civilization, leaving only scattered survivors to rebuild from the fragments of a drowned world. From the precision-engineered monuments that encode astronomical knowledge to the sophisticated underwater structures mapping our lost continental shelves, the evidence points to a truth that mainstream archaeology isn't ready to accept. We may not be the first advanced civilization this planet has seen. The flood stories that echo across every culture on Earth aren't mythology. They're the preserved memories of our species' greatest tragedy and most remarkable recovery. The question isn't whether this happened, but whether we're wise enough to learn from it before the cycle repeats itself.